Hello everyone, my name is Anukul and this is my capstone presentation titled Data Informed Crime Forecasting and Response in Chicago. Over the past 7 weeks, I have built a predictive and fairness aware framework to help allocation police patrols based on crime forecastings. This project brings together data science, ethics, public safety strategy, and I'm excited to walk you through. Chicago faces persistent challenges with crime, particularly in certain neighborhoods. Traditional reactive policing can lead to the insufficient coverage or even over policing in vulnerable communities. My goal was to build a data driven system that predicts crime trends and allocate patrols fairly. The significance here is twofold: improving safety outcomes while promoting ethical, equitable deployment of policing resources. This project follows a structural 3 weeks process. I started with collecting and cleaning crime data from the city of Chicago, then moved through the explanatory analysis, spatial and temporal modeling, predictive modeling, and finally patrol allocations. The work is grounded in theories like routine active theory and Wishbart's law of crime concentration, which suggests crime happens when opportunity arises and tend to cluster in specific place and times. The dataset used for this project come from the City of Chicago Open Data Portal and includes over 7 million crime incident recorded from 2001 to 2025. I clean and process this data using Python libraries like Pandas and GeoPandas. This, this involves parsing data fields, handling missing values, uh, removing the duplicate values, and align each incident with one of the Chicago's 55 Chicago 77 community areas. On the right, you can see a heat map that overlay crime intensity across Chicago. This map generated using kernel density estimations provide a high-level view of where crime incidents were historically concentrated. It was used early in the project to confirm the data coverage, guide deeper spatial analysis. You'll notice bright red regions in the south and the west side, which are known for higher crime volumes. During the explanatory phases, I examined the trends in s- crimes categories, frequencies over times, and spatial distributions across Chicago. This helped determine how crime is structured and what variables should be included in the predictive models. I used tools like Seaborn's matplotlibs to generate visualizations. On the right, the bar charts show the distribution of crime types in Chicago. Property crimes include the theft, burglary are the most common, followed by the violence crimes like battery. Other crime, which include the offensive such as narcotics and weapon violations, also make a significant portions. This breakdown helps prioritize which patterns to focus on in the later stage. To analyze the temporal trends, I use the Prophet library, which is well suited for identifying seasonality and recurring patterns in time series data. I discovered that crime activities in Chicago peak during the summer month, especially in July, and typically decline during the winter. Additionally, crime tend to occur more frequently between 3 p.m. and 8 p.m., particularly on the weekends, which align with the routine activity theory. The chart on the right shows the monthly crime trends across the multiple years. Each line represents a different years, which with the red indicating the higher crime totals and the green indicating the lower ones. As you can see, there is a consistent seasonal peak in July and uh, a valley around January. This insight support the use of crime-based features in our predictive models. For the geospatial analysis, I use two complementary methods, kernel density estimations KDE to visualize general area of crime concentration and JTIS-ORDGI statistics to identify statistically significant clusters or hotspots. This helps pinpoint communities most in need of focus, attention, and resources. The heat map on the right displays the crime density across Chicago with red area indicating the higher incident concentrations. You can see prominently hot zones along with the west and south side, especially in the neighborhoods like Austin, Eaglewood, and part of the Loop. This spatial insight was critical in guiding both the predictive model and patrol allocation strategy. To forecast the daily crime counts for each community area over a 30 days horizon, I trained two machine learning models, random forest and gradient boosting. I use time series across cross validations to ensure temporal consistency and prevent data leakage. The model relies on the features like clinical encodings of data and community identifiers without a lag variables which were excluded based on the instructor feedback. The scatter plot on the right shows the predicted crime counts versus the actual values for the test set. Most points align closely along the diagonal, indicating the strong model performance. While there are some variability at higher crime counts, the overall trend suggests the model captured the patterns well, particularly in the lower to the mid-range predictive bands. Along the two models tested, gradient boosting emerged as the top performers with the mean absolute error of approximately 2.672 and a high R square score on the test set. This suggests the model explained a significant portion of the variance in crime counts across community areas. The bar chart shows the top predictors ranked by their importance in the final models. The most influential features were specific community areas like areas 25, 8, and 28, which consistently experience higher crime volumes. Temporal features such as year, month, day of the week, insudial encoding also played a key role. This results highlights both spatial and temporal patterns are essential for accurate forecasting. The final step of the project involves translating forecasts into actionable patrol plans. I developed a proportional allocation algorithm that distributes 300 patrol units each day across Chicago community area based on predicted crime volumes. To ensure equity, I applied a fairness constraint that capped allocation at 3%, which equals 9 units per area, preventing overpolicing of any single neighborhood. The bar chart on the right displays the top 10 communities area by average patrol allocations over the forecast period. The red dashes line indicate the 9 units cap. You can see that while some areas consistently receive a high allocations, none exceeded the fairness thresholds. This mechanism reinforces operational balance between effectiveness and ethical constraints. Interactive maps and a risk timeline were also created to help visualizations, daily deployments, and surge needed. Ethics were at the core of this project. I deliberately excluded demographic and socioeconomic variables to reduce the risk of encoding historical biases. I also enforces the fairness constraints like 3% patrol cap per area and conducted allocations audit to ensure no community was unfairly burdened or neglected. These choices were guided by the fairness literature such as Lum and Isaac 2016 and Broca's et al. 2019. The sample heat map screenshot on the right visualize the community level patrols allocations. Larger red dots indicate areas with higher units assigned, but all remains within the fairness threshold. The color shading represent relative crime risks. This transparent visualization helps stakeholders understand and verify the fairness of the distribution strategy, making the model more acceptable for the real world use. In summary, this project demonstrated how we can responsibly apply the machine learnings and geospatial analysis to improve crime forecasting and resources allocations. It produced accurate 30 days forecast and generated equitable patrol schedules grounded in theory and ethics. It showed the data science can support public safety without compromising fairness. The next step include integrating real-time data such as weather or 911 call trends to capture short-term anomalies. I'd also like to conduct a more in-depth fairness audit and eventually build a real-time dashboard for operational use. Exploring more advanced models like LSTMs could also further improve the forecasting accuracy. One of the biggest challenges was handling such a large set of data with the limited computing resources. I use mostly Google Colabs to overcome these limitations. The most rewarding part was seeing the forecast actually drive operational output, transforming predictions into a patrol schedules. A key takeaway is that ethical considerations must be integrated early and consistently in any data science project, especially in sensitive area like policing. Due to the memory limitations, I had to limit my test to limited data and produce a sample visualizations rather than the actual visualizations from the whole set of data. That is all for this presentation. Thank you.